I will begin. I will begin. Dear Father, we thank you for this day, and thank you for the students, even those who couldn't be here for reasons unknown. Help us to have a good class today. Help us to glorify you, what we do, and just to learn lots about polar coordinates. In the name of prayer, Lord Jesus. Amen. All right, so let me get right to it. Polar coordinates and their calculus. So I'll start with the polar coordinates. The main point here is that the equations that we introduce are, well, I'll tell you what, I'll work it out here for a second. So let's look at a picture. If we take a point here, let's say x comma y, then we can measure the standard angle, theta, measured from the positive x-axis in the counterclockwise sense, like that. And if you look at this, it's fairly obvious that if we let r equal to the square root of x squared plus y squared here, right? Then if you look, of course, right triangle trigonometry, you can see that the x and the y coordinates, from this right triangle here, we'd have y equals to r sine theta, and we'd have x equals to r cosine theta, right? So this suggests that we introduce polar coordinates. So we can let r equal to the square root of x squared plus y squared, and theta be the standard angle, counterclockwise measured angle off the positive x-axis. All right. Given that setup, the relation between r and theta and x and y is as follows. X is equal to r cosine theta, y is equal to r sine theta. These are polar coordinates. Now, the neat thing is, while I have started by drawing this point in quadrant 1, right, these formulas continue to make sense in quadrants 2, 3, and 4, right? Like over here, if I pick a point in quadrant 2, well, let me make a new picture. So, I motivated via quadrant 1, right, where 0 is less than theta is less than pi over 2, right? And so there we have sine theta and cosine theta both positive, right? In quadrant 1, both sine and cosine are positive. But if I was to make a picture, right, with the other quadrants, I could make a picture and I could say, okay, so here we've got cosine theta and we got sine theta. They're both positive, right? How about over here? What's the deal with cosine theta and sine theta? Right, and so this is for pi over 2 less than theta less than pi, right? Over here we have, you say cosine's negative and sine's positive, right? In quadrant 3, where we have pi less than theta less than 3 pi over 2, right? Down here we've got what? We've got, yeah, they're both negative. And then finally in quadrant 4, right? For some reason we use Roman enumeration for the quadrants. Hardly anything else but quadrants, Roman numerals usually. And so there, of course, you got 3 pi over 2 less than theta less than 2 pi. And there we have cosine theta positive, right? And sine theta negative. of course, these choices of sign, like plus or minus, are exactly what you know from your study of trigonometry, right? And it's no accident. We define sine and cosine beyond acute angles precisely so that polar coordinates work. It's not probably why we define sine and cosine as we do, if I may be honest. Well, that's one reason. But anyway, if you read your textbook and, well, anyway, he says that r is the directed distance. All right, so the definition I just gave you here of r would not be a directed distance. That would just be what I would say is the standard polar coordinate. All right, and you got to be careful here. There's there's an ambiguity that exists in textbooks. Some textbooks allow r to be positive and negative. Some textbooks allow force r to be positive. In Calculus 3, I insist that r is positive or non-negative. So in Calculus 3, I require that r is the square root of x squared plus y squared, personally. That's so that polar coordinates are not so ambiguous. But in this section, in chapter 10 of the book, he does not do that. He says that r is the directed distance. And what that means is that he allows r to equal to plus or minus the square root of x squared plus y squared. All right? And the way this works is that if I have the point here, which is, at r comma theta, right? And if you don't mind, I'm going to say it's at r comma theta. I'm going to write a little subpolar here just to be clear. So this I don't even want to say it that way. I'm sorry, guys. Let me get this out of my system here. Let me pick a specific point. That'd be easier here. Example. Consider the point 1, 1. Cartesian coordinates, okay? By default, if I give you a pair of things, Cartesian, I don't write sub-Cartesian because we work in Cartesian as default, right? In other words, I mean the point in R2 with x equals to 1 and y equals to 1, right? So the thing is, how can we get 1 is equal to r cosine theta and 1 is equal to r sine theta, right? What r and theta allow you to get 1 there? Well, I gotta get both or 1, right? So this point right here is at 45 degrees, right? So one solution would be theta equals to pi over 4, right? And r equals to square root of 1 squared plus 1 squared, right? Square root of 2. So the point 1, 1 has polar coordinates pi over square root of 2 and pi over 4, right? So we could say this, 1, 1 corresponds to the square root of 2, pi over 4 in polars. I'm going to write that little subpolar until I get really tired of it, because I think it's helpful. But is there another choice of theta and r you could do here, which would also get you 1 and 1? How about over here, we've got cosine of 5 pi over 4 equals to minus 1 over root 2. And sine of pi over 4, 5 pi over 4, you know what that is equal to? Minus 1 over root 2, right? So if you look at it, this is also interchangeable with the point square root of, well, not square root of 2, but minus the square root of 2, comma 5 pi over 4. See, because if you put this minus root 2 up here, and you put 5 pi over 4 up here, you'll still get 1 and 1, right? So we could use polar coordinates minus root 2, comma 5 pi over 4 polar coordinates, right? And that would also represent the Cartesian point 1, 1. But it's worse. I mean, like, let's see here. Let me just try to. He has a nice, actually, I was happy with the book. He actually gave us something useful in this regard. So he has a nice list of equivalent polar points, you might say. So first, this one's kind of less controversial, and I would also allow this in Calculus 3. Our theta is the same geometric point, right? Geometrically as, and here he has r comma 2 pi plus theta. Right? If you shift the standard angle by 2 pi, you're still at the same place. But of course, and then the other thing, of course, we could do, and I was just illustrating this, is that our theta is equivalent to minus r comma theta plus pi. See, that's what I just did with pi over 4 plus pi is 5 pi over 4. So I just illustrated that second equivalence with my example 1. And so that's it. Let me just keep it at that. Of course, you can add more multiples of pi, and you could do this. I mean, like, you can combine these ideas, right? I mean, this is almost never relevant, but you could do this too, right? Let me say something more interesting, okay? So, example 2. If I wanted to describe the shaded region via polar coordinates and Cartesian coordinates. I'll do the easy part. Cartesian. So Cartesian, we have x greater than or equal to 0. I'm throwing in the y-axis, okay? The y-axis would be x equal to 0, right? So how would you describe that in terms of polar coordinates? So here I'm going to demand that r is greater than or equal to 0, because otherwise it's weird. That's the thing. I, by default, assume r is positive when I make comments in here. So to me, it's very annoying that the book allows r to be negative for the sake of certain problems. But it is a custom. It's not just the book, it's engineers too. And yeah, well, anyway. All right, so how would you describe this? I mean, you could do, it's like from here to here, right? So that would be what? That would be 0 less than or equal to theta less than or equal to pi over 2. And, or I really shouldn't say and, I should say or, down here, right? This is 3 pi over 2, right? Or I could say 3 pi over 2 less than theta less than equal to 2 pi, right? Now, including 0 in both double counts the x-axis, but I'm not particularly bothered by that, right? But now, suppose you're, and we will be very soon doing this, doing an integration, which is based on integrating in quadrants 1 and 4. So when we set up things, we'll end up integrating over theta. Do you want to integrate from 0 to pi over 2 and then do a separate integral for 3 pi over 2 to 2 pi? No, you do not. So what's a better way to describe this in terms of polar coordinates with r positive? You just go, yeah, negative pi over 2 less than or equal to theta less than or equal to pi over 2. Or, what are you going to say? 0 to 2 pi. But I suppose you could also, the competing, I would say you could do 3 pi over 2 less than or equal to theta less than or equal to sorry, I'll get it out of my system here. This is pi over 2, but geometrically that's the same as, yes, 5, thank you, 5 pi over 2. I can't do math. And see, this is interchangeable with minus pi over 2, right? So you could also trade this for 3 pi over 2 to 5 pi over 2, but nobody does this, you know, because if you're integrating, integration loves this. That's the thing to integrate. Now, there's danger here. If I tell you something like, if I said something like integrate theta, d theta, you know, over r, and this whole region was r, right? Well, that problem doesn't make sense unless I tell you which theta I'm talking about. Because that integral is going to be different depending on whether theta ranges from minus pi over 2 to pi over 2 or to 3 pi over 2 to 5 pi over 2. So watch out for problems like that. Every once in a while they creep up on you. They're mostly made by me, but every once in a while one of them will slip into a book. Anyway, now I'm talking about like second or third order logic here. Let's get back to the basics, okay? So we have polar coordinates. We can describe a point in the plane either with Cartesian coordinates or with polar coordinates. The next thing you want to talk about is, and I'll let your homework will teach you how to actually change Cartesians to polars and vice versa. We lost a day or two, so I'm not going to do that in class, but yeah.
I was just wondering, why would the integral for the same area be different when it's represented differently?
Because theta is ambiguous. If I'm saying theta can either be a variable which is ranging between minus pi over 2 and pi over 2, or 3 pi over 2 and 5 pi over 2, those are quite different thetas. The integral of x from minus pi over 2 to pi over 2 dx is different than the integral of x dx from 3 pi over 2 to 5 pi over 2. One of those is 0, I think. One of those is not. But let me stop. Listen, whenever in math we decide to identify different things as being the same, it comes with baggage. And if you forget that that baggage is there, you can get really, really confused. So I'm just warning you that this is, you know, that's the deal. Directed distance, because directed distance means that it can either be positive or negative. Just like we had a directed distance for the p in section 10.1 we learned. P could be positive or negative, depending on whether it's a positive direction or a negative direction in the natural way. Okay, so let's get to something more interesting. How to describe curves via polar coordinates, right? So let's just look at some examples. I think is the best thing to do. Example 3, I'll start out with something really easy. Suppose you had x squared plus y squared equals to 9. What is this in polar coordinates? So what you, yeah, plug in, we get r cosine theta squared, right? R sine theta squared equal to 9. So you get sine squared plus cosine squared, which is? Right? So we get r squared is 9. So I would say that this implies that r is equal to 3. Admittedly, algebraically, it could be minus 3. And that would also be meaningful here. Well, I'm just going to say 3 because that makes me happier. What about theta? Theta's free, right? That's what a circle is, right? We could put plus or minus 3 there. I just think it's weird. I mean, this, admittedly, minus 3 is also a solution given our agreement that r is a directed distance. It's just r equals minus 3 will cease being a legitimate answer in my calculus 3 course, for example. Sorry. I don't know. Let me say it a different way. R equals 3 covers the whole curve. So throwing in minus 3 is just redundant. You know? Maybe that's a better way to get to it. How about example 4? Example 4, I've got x squared plus y squared equals to 9. And y is greater than or equal to x. What's that look like? Here I would take a graphical approach, right? We already know it's the circle, 3, radius 3, right? And we're looking for points on the circle with y greater than x, right? So here's y equals to x, right? Where is y greater than x? How do you graph that inequality? Right. Yeah, above the line, exactly. So it's up here. So we're looking for the curve, this curve right here, right? So we should say, okay, so it's r equals to 3. Same logic as I just had up here, because if we convert the Cartesian equation to polars, it just simplifies to r equals to 3. And the other reason I want to do that is if I said r equals minus 3, then I got to think about the weird non-standard standard angle. Why do we even talk about it? I'm sorry. We will stop talking about it as soon as I finish writing my notes for Calculus 2. I will never speak these words again in future offerings. As soon as I finish writing my notes for this silly course, then I will ignore it, pretend, I will censor it from the course, discussion of negative r. Pi over 4 less than or equal to theta, less than or equal to what? So this is pi over 4. How do I know that? Because I know the line y equals x is 45 degrees, which is pi over 4 in radians, right? So what you got, Tamara? What's this? What's that angle? More than pi. 5 pi over 4. Yeah. And that would be the polar description of this arc of the circle. Does that make sense? It gets weirder. Example 5. Let's consider the line y equals 2x minus 1. Find the polar description. It's kind of funny. A student was complaining to me, not you guys. Who was it? I can't remember, but they had a funny comment, like in Cartesian variables, right? Or in your book, rectangular. If we're going to find one variable as a function of the other, what do we solve for? y, right? We find y as a function of x predominantly. And yet, in the polar context, it's customary to find r as a function of theta, which is kind of funny because we think of them as r comma theta, you know, polar versus x comma y, rectangular, but I never write the rectangular because it's our default. But I feel like r theta demands a subpolar to warn you I'm talking about polar coordinates, yeah? Okay, so how do I do it? Same thing I did in the last one. What I do is I just take y and I plug in r sine theta equals to 2, x is r cosine theta, I subtract 1, right? That gives me the equation of the curve in polar coordinates, but I'd like to find r as a function of theta. That's what we try to do if we can. So solving for r, this gives me, I isolate r, so that gives me r sine theta minus 2r cosine theta equals minus 1. Factor out the r. We get r times sine theta minus 2 cosine theta equals to minus 1. So finally, we get r is equal to 1 over 2 cosine theta minus sine theta.
What did the negative 1 do?
I flippity-floppited.
Oh.
So this right here is what you might call a polar graph. In other words, I give r as a function of theta. Moral of the story here, if you're going to describe a line, should you use polar coordinates or should you use Cartesian coordinates given the freedom? Which
Maybe polar?
so Brian's not here, so you're like taking over for him. It's like,
Oh, no.
no, the point here is this is awful, right?
Yeah.
This is horrible. This is a terrible, terrible equation. This, on the other hand, is linear. I mean, it's nice. It's elegant. So lines really belong to Cartesian equations. In contrast, over here, in Cartesian, I would argue this is quite ugly, right? We actually have to split it into two cases. If I find y, we have to split it into y equals to plus or minus the square root of 9 minus x squared, right, to get the upper and lower half of the circle. I mean, it's a pain. And in contrast, in polar coordinates, this thing is r equal to 3. It's so much nicer, right? What's a vertical line look like in polar coordinates? I'll fit it in the middle here. Suppose I had x equals to 7. What's that look like in polar coordinates? That's r cosine theta is equal to 7, which is to say that r is equal to 7 over cosine theta. So x equals to 7, a vertical line in Cartesian. In polar coordinates, it becomes r is equal to 7 secant theta. Ugh, that is not cool. Obviously, you want to use Cartesian variables for vertical lines. All right, so let's do something which is a little bit less nice. Let's see here. So let's see here. What's the calculational process I'm trying to introduce you guys to? To convert from a Cartesian formulation to a polar formulation, all we do is we plug in these fundamental equations, x equals r cosine theta, y equals r sine theta, into the equation and see what happens. Yeah?
Would that be, if it was hyperbolic, would it be x equals cosh and y equals?
You know, hyperbolic coordinates are not widely used, so we don't talk about them.
It's for a question.
Oh, yeah, well, that's what's for your homework, I suppose, then. What did I ask you? I asked you about hyperbolic coordinates in homework?
Yeah.
Oh. Or
I'm
in the
pretty
book?
sure it's hyperbolic, Mark, doing something.
What we talk about? Which problem?
But,
Is this in the book?
yeah.
Oh, then it's not what I'm thinking of. What I'm thinking of would be in the book. Which one are you talking about?
Number 10.2, number 50, or, no, no, 10.2, number 320, 48. Number 48.
Oh, but that's parameterizing.
Yeah.
Well, yeah, I mean, there you just need to find the equation. So there, all you got to do.
Isn't that sin squared minus cos squared?
I wouldn't know without getting into it, but I would go back to 10.1. It's either sinh and cosh or cosh and sinh, but
Either way, when I graph it, it just
so
loses, like,
for 48, what I would do is I would go back to 10.1, and I would sort through the equations for vertices and focal points, and that will allow me to find the Cartesian equation, at which point I can use the things I wrote on the board in here to write down the parameterization, right? Depending on whether it's x squared minus y squared kind of thing, or if it's a y squared minus x squared kind of thing. But yeah, it should be cosh and sinh. Those are not coordinates, though. That's a parameterization. I mean, what I was thinking about, Josh, is you might investigate something like x is equal to rho cosh phi and y is equal to rho sinh phi. You might do something like that for like hyperbolic coordinates. But these are actually somewhat complicated and not that nice. And that formula only makes sense for like a certain region. So it doesn't work out as nice as polar coordinates. It actually, if you tried to do something like this, it kind of only works on a sector between like y equals plus or minus x. And it has something to do with like light cones and special relativity. But anyway, let me get back on track here. Okay, so example 7, you could have something like this. X squared plus 4x plus y squared equals to 10. And you could say, what's that in, try to find the polar equation of that. Now, so the other thing I was going to remark is that these are nice, but you know what else is nice? What else is nice is noticing, just as a means of not reinventing the wheel 1,000 times, is that x squared plus y squared is r squared, right? So this is something that we really should just have on tap to use. You don't want to have to keep working that out again and again and again, right? And the other thing that's kind of nice to notice is that the tangent of theta is y over x, right? So these are sometimes helpful. Of course, that assumes x not 0, right? So in view of that, I can take this x squared and y squared and trade it for an r squared. And the 4x is what? It's going to be 4r cosine theta equals to 10. Now, if I'm just looking for a polar equation for the curve, you're looking at it. Right, that's it. If I wanted to find r as a function of theta here, I'd have to work a little bit harder. So to find r as a function of theta, what would we do? Yeah, in fact, that's exactly what we do, is think about it as a quadratic equation. Very good. So this is r squared plus 2 cosine theta, rather r plus 2 cosine theta squared. Let me put down another step. I'm jumping too far ahead. So right here. So this would be r squared plus 4r cosine theta minus 10 equals to 0. And if I wanted this, so I complete the square. Tell you what, I'll need this quadratic equation. Why not? R is minus 4 cosine theta plus or minus the square root of 16 cosine squared theta minus 4 times minus 10 divided by 2. So we get r is equal to minus 2 cosine theta plus or minus the square root of 4 cosine squared theta plus 10. What I did there, guys, is I brought the 2 inside the square root. That gives me a fourth. See, division by 2 into a square root. If I got a square root of stuff divided by 2, that's equal to the square root of 1/4 times the stuff. Because 2 is the square root of 4, so I can bring it inside using laws of exponents. And then that 4 makes that 16 into a 4 and makes the 4 into a 1 and then make it 10. But so yeah, there's r as a function of theta there. Now, how should we think about this curve? Like, what's the best way to think about this curve? I think the best way would be to complete the square in Cartesians. If I actually want to graph this thing, what I would do is I would go back to like section 10.1 kind of thinking, which is that this is x plus 2 quantity squared, right? Plus y squared equals to what? (14). In other words, this is a circle at minus 2 comma 0 with radius square root of 14. And then I could be so foolish as to try to graph that, minus 2, 0. And how big is square root of 14? It's big enough that I regret drawing that scale. I mean, it's between 3 and 4, right? Curses. So let me make this the minus 2. There we go. So there's my center. So something like this. I was kind of hoping that when I did that, I might get some better sense of why there was a plus and minus in the radial solution. But I don't see it right off. It's possible that only one of those is required if you let theta range over the proper, maybe if we let theta range from 0 to 2 pi, it covers the whole circle. And this is just kind of this again, but in a more complicated context. I don't know. I'd have to actually use some graphing utility to actually decide on that. All right, so there you go, a harder example. And now I want to look at some more, turn the tables here. I've been starting with Cartesian and going to polar, right? What if we go the other way? What if instead we think about, given a polar equation, graphing it? Now, some of them we could do would be really easy. Let's start out with the easy ones, okay? So example 8. I say plot theta squared equal to pi squared over 9. So solve for theta. What's this give us? We get plus or minus pi over 3, right? So this is actually kind of a kind of funky thing. It's a pair of rays, right? One ray at pi over 3, and the other one, that's supposed to be pi over 3. I tried, but maybe it's more like that. They're pi over 3. Right? And then the other one down here. So the plot of this is just 2 rays that go off to infinity like that. That's what that is, right? Example 9. What if I had, let's say, r cosine theta minus r sine theta equals to 2. I want to plot that polar equation. What's that? This is what? X minus y equals to 2. Right, very good. Therefore, y is equal to what? X minus 2. So, yeah, the smart way to do that would be just what you did. Very good. It doesn't have to be complicated, right? But sometimes, when you're given something in polar coordinates, it's actually something genuinely new. All right? So let me show you some of those and give you a technique for graphing. So, we always fall back on what we already know when we can get away with it. But sometimes there are things that you just haven't seen yet. All right? So let me show you some pretty ones of those. Oh. So one bad thing about cutting the book into pieces is then you can lose pieces. If I tell you it felt good. I should have done it in class. I firmly believe it improves course evaluations if you tear pieces out of books in front of students. Like, it's definitely a win. Let's see here. All right, let's look at stupid book. Cramping my style. Yeah, that's a good one. Example 10. We could look at, I already forgot it. Sorry. Good grief. R equals to sine theta. All right. R equals to sine theta for 0 to pi. All right. So let me show you my method. This is the method I use to do these kinds of problems. I could take an algebraic approach. That would actually be there's two approaches. Here's the boring algebraic approach. Multiply by r. Right? Multiply by r. Multiplying by r gives me what? X squared plus y squared equals to y. Right? Which gives me that x squared plus y squared minus y equals to 0, which gives me that x squared plus parentheses y minus 1/2 squared equals to 1/4 by completing the square. Lo and behold, it's a circle, radius 1/2, and it's centered at 0, 1/2. That's not a bad way to do this one. It's faster than what I'm about to show you. But there are limitations to this method. This method only works out well for you if when you convert back to Cartesian equations, it's actually something you can recognize, right? If you can't recognize what you get back to, then this isn't really any help at all. But of course, this is a circle centered at 0, 1/2. But let's look at the more general way to do this, okay? So here's my other way. You make a graph in theta r plane in the sense that I put r this way, okay? I put theta this way. All right? And I plot r as a function of theta as I'm given. Here I'm given sine theta. What's sine theta look like from 0 to 0 to pi? That's it, right? This is r equals to sine theta, all right? And then I use this to plot the curve in the Cartesian context. And the way I do it is I just follow, I pick points on my polar graph, and I translate those into what they mean on the Cartesian graph. So let's just pick some points. Let's give them labels. Let's track them. Point 1, point 2, 3, 4, and finally 5. Point 1 has theta equals to 0 and r equals to 0. That is the origin down here, right? Now I go to 2. Let's suppose that 2 is, pi over 4, pi over 2, 3 pi over 4, pi, okay? Pi over 4 gives me sine of pi over 4, which is 1 over root 2, right? But pi over 4 is where here geometrically? It's like this, right? And over here is the 3 pi over 4. Okay? So if this, so point 2 would give me, roughly speaking, I mean, I can even do it to scale if I want to. I don't always insist on that, but there's 2. It's at pi over 4, and it's 1 over root 2 away from the origin. How about 3? 3, up here, it's the point, well, let me not write more. 3 is where r is equal to 1, and theta is pi over 2, right? So pi over 2 is the y-axis, and 1, well, 3, right? Now point 4, I can't do. I've not drawn these, well, anyway, I tried. My picture doesn't always come out so great, but you got the idea. Where's 5? What's sine of pi? 0. So we're back to the origin again. And see what you got here is a badly drawn circle. So. Shall we do another? Let's do another example. This one will not be amenable. Not a word. Amenable. Yeah. Let's try r equals to sine of 2 theta. All right. This time, my Cartesian trick is out the window. Right? Even if I was to somehow switch this over to Cartesians, it wouldn't be nice algebraically. So what I have to use this method. So I plot, and this time I'm going to say 0 less than or equal to theta less than or equal to 2 pi. Okay? So I'm going to actually, and that actually, we're going to cut that down. I think I can just cut that, well, we may learn that we don't need all of that, all right? So let's agree that we're going to cut that interval of theta down once we start reinventing the wheel, so to speak.
Does the book show that method or just the Cartesian?
I'm sure the book has something like it. I mean, he tries to, in example 4, I don't see it there. He makes tables of values for r and theta. I don't see him actually graphing. Frankly, I don't care. I mean, sorry, but
Is that what he does for example 5?
no, not really. He just does it bit by bit. I mean, so the thing he's creating in the picture in example 4, you're talking about 4, I think.
Are you on 10.4?
Yeah? Example what?
I was looking at example 5. Example 4 looks weird.
Example 4 is somewhat indicative of what I'm doing at the moment. Example 5 is involving calculus we haven't covered yet. Give me 20 minutes. If I have them. All right, let's get on with it here. So sine 2 theta. I need to plot this. No, in short, shockingly, the book is missing an important technique which should be shared with students. Surprise, surprise. Okay, so our theta, sine 2 theta, what's that look like? Well, we can graph that. And sine 2 theta actually looks like this, right? So it's fairly obvious we're not going to need all of that theta to get the whole story, are we? Let me just stick with it, though. I'm not going to stick with it. Let me stick with it. Stick with it. And so, okay. I'll use a color coding approach this time. I mean, let's think about this first. Where is this? This is pi over 2, right? So geometrically, I mean, you can think about this as what's happening in quadrant 1 in principle, in quadrant 2 in principle, right? In quadrant 3 in principle, in quadrant 4 in principle. I say in principle because r is negative there, which means actually geometrically it's not going to be in quadrants 2 and 4. It's actually going to be in the polar opposite quadrants. But let's focus on 1 here. So we're starting at angle 0, right? Angle 0, angle pi over 2. So that's basically in here, right? And what happens? To get from here to here, I'll use color coding here. We're starting at 0, we'll swing out to some maximum radius, and then we come back. Like that. That's from 1. Then 3, in principle 3 would be here, right? But in practice, it's not because r is less than 0, right? So instead of actually being quadrant 2, we use that reflection, the fact that theta is, the r is negative, puts us over here. So we continue this picture like so. This is from 2. Okay, this is from 1. What happens in 3? I'll use green. 3, r is positive, so geometrically things are nice, right? And where's that going to, so quadrant 3, which is where? Down here, right? So we swing out, and then back again, right? That brings us to quadrant 4. Apparently I did need 0 to 2 pi to get the full story, right? Which I'll do in black. So then that swings out here like this, and then back. And that was supposed to be the same as the others, but oh well. Mine are reasonably symmetric given the limits of my artistry. So there you go. It's a 4-petaled flower or something. This is what our sine 2 theta looks like. What's the Cartesian equation of this? I mean, I can figure it out now. It's square root of x squared. Well, let me multiply by. I got r squared equals to r sine 2 theta, right? Which is r times 1/2 of sine theta cosine theta, right? Which means that x squared plus y squared is equal to x squared plus y squared equals to, let's say, y over 2 times x over the square root of x squared plus y squared. There you go. everyone knows that the solution set to that Cartesian equation is a four-petaled rose, right? No, we've never seen that before, have we? Right. But for kicks, you could chuck this into Wolfram alpha and see if it looks like that, right? Now, once you know this, you can't help yourself but to study other things like this, right? Like what happens if you put a 3 there? Or what happens if you use cosine instead, right? What if we did like r is equal to cosine of 3 theta? What would that look like? So graph cosine 3 theta, what's it look like? Let's see here. Sorry, I can't do cosine. I don't know, it's the same stupid curve, but I have trouble with cosine. What's wrong with me? Let's see here. Ah, even worse. This is a sign I should get the projector out, isn't it? Let's see here. All right, roughly speaking. So, 3 theta equals to pi over 2. That's the first place that this is 0, which is actually what? Theta equals to pi over 6, right? So this is actually pi over 6. This is minus pi over 6. And what's this here? I guess I could ask the question, what's that? What's that? I think that should be 2 pi over 3, right?
Oh, yeah.
Because we're back to where we started, and this has it's compressed 3. So 2 pi becomes 2 pi over 3 for cosine 3 theta in terms of the graphing. This guy over here, 4 pi over 3. Right? So what's this here, this tick mark? These humps, how wide are they? Oh, we can see it from here easily, right? 2 pi over 6, in other words, pi over 3. So this should be pi over 6 plus pi over 3, which is what? Pi over 6 plus pi over 3 is what? 3 pi over 6, right? AKA pi over 2. Anyway, you need to get your bearings on the graph. Once you have that, it's pretty easy to make the corresponding actual graph in the Cartesian plane for this curve. So it helps me out to use some color coding here. This red one, it's happening between the rays plus or minus pi over 6, right? Those are sort of your guidelines through this initial loop. So you're going like this. And then how about the next one? Where's that? That's negative, right? So in principle, this piece right here, right, would be between pi over 6 and pi. It would be up in here, right? But in fact, you end up back here because you have to reflect through the origin, right? See, it would be between pi over 6 up to pi over 2, but r is negative, so I flip down there. And it goes like so. Then that brings me to this third piece over here, right? Pi over 2